Hi, I'm Reid Prichard, and today I'm going to be telling you about a novel methodology we devised for the optimization of high-performance computing resources. First, let's talk a little bit about the optimization problem and why optimization is necessary. High-performance computing is a vital tool for computational research. Lots of scientific codes are quite expensive, and in particular, we heavily use computational fluid dynamics. In our research, we are using HPC every day and it's vital to our workflow. The downside of that power is that HPC can be extremely expensive. So a single simulation for us usually costs in the range of $10,000 to $100,000, and it can take weeks, months, or even years depending on the scale of the simulation to obtain those results. When you're talking about numbers this large, optimization is crucial. Even a few percent is going to save you, thousands of dollars and days of time. And in reality, we found that with our optimization, we're often saving, 10, 20, 30%. So the savings from that optimization process are just absolutely enormous. When optimizing HPC, you have two basic objectives. The first is to minimize the number of core hours used, which means cheaper results, and the second is to minimize the number of Earth hours, so faster results. To bring about these objectives, there are several variables that you can manipulate. The first is machine type. With cloud service providers, there are usually many types of different compute nodes that can be used for your research. Now, some of these might be denoted as, being specialized in certain tasks other than scientific computing. But there are still usually several machine types that are advertised as being suited to HPC. You don't really know which of those will be best for any given problem until you actually go through the process of testing and optimization. The second variable you can control is machine count. This is almost a new freedom with cloud computing, is that you can really provision any number of machines you want. It's effectively limitless. So you could choose to run a simulation on one machine, or you could choose to run it on 100 machines, and there's really no way of knowing where in that range is going to be the best for your particular objectives until you do the testing and optimization process. The final variable is something called undersubscription. It's pretty well known in the literature that counterintuitively, if you leave a few cores unused on a computer, you can often speed up the results substantially. So we've seen improvements from this in the 10 to 20% range, although several percent is usually a more realistic number. There's no way of knowing what the ideal undersubscription is, though, until you actually go through the testing and optimization process. So it's an important thing to consider as well. One thing that makes optimization difficult is that this is multi-objective optimization. As I mentioned, we have those two objectives of cost and speed, which means that there is no single best solution. You will likely have one that is the fastest, you will have one that is the slowest, or that is the cheapest, and then you'll have a spectrum of different permutations that are somewhere in between there that give you various compromises of those two objectives. The particular best for your situation will just depend on your current needs. So if you have a paper due in 2 weeks and you need to get a lot of results in that time frame, speed is going to be your more important objective. But if you're on a really tight budget, cost is going to be more important, and you might choose a different permutation than if speed were the most important. So because you're constantly having to look at this data and kind of reevaluate, you might have to move around from one to another as your needs change over time, the data must be presented in an easily understandable form. You need to be able to look at it and very quickly say, okay, based on my current objectives, here is the best combination of variables for what I need to accomplish. If we just take this data and throw it into a regular, XY scatter plot as seen on the right, there's not a whole lot of value seen there. So, you can look at that and we see that the square markers are benchmark duration. So looking at that plot, you can see, okay, well, there's one particular point where benchmark duration is least. That's going to be the fastest. But it's hard to really judge any of the other points. You can tell the relative speed, but you can't tell the relative cost, and it's just kind of a mess to try to glean much other than what is the fastest from this one plot. So to try to clean this up, the first thing we're going to go through is normalization. The first variable we're going to create, we call the normalized runtime. The normalized runtime indicates the time required to compute 1 second of solution time. So it's just this ratio of the benchmark duration, the number of Earth seconds that elapsed in the benchmark, divided by the computed solution time. So, if your benchmark took 10 seconds and it computed 1 second of solution time, that value would be 10. Now, this is geared toward transient simulations, but if you were to have a steady state simulation, you could just replace that computed solution time with the number of iterations computed. Now, cost is a little bit more challenging because in the previous plot, we were looking at hardware hourly cost. Now, as kind of a initial feel for things, it seems like, okay, hourly cost, yeah, that's a pretty good indicator of how much it's going to cost. But the hourly cost doesn't indicate the total cost. The total cost also depends on the simulation speed. So if you had two options and one were twice as fast but cost twice as much per hour, the two would cost the same because that increase in hourly cost is offset by the increase in speed. So normalized cost takes the normalized runtime into consideration to remove that from the equation. So you can see that the normalized cost indicates the cost to compute 1 second of solution time and is formulated as the cost of one node per hour times the node count, which is effectively just your cluster's hourly cost, times the normalized runtime, and then we do a little unit conversion from hours to seconds. Both of these quantities, we want to decrease them. So if your normalized runtime decreases, it will compute in less time and proportionally so. So if you have your normalized runtime, your simulation is going to take half as long. And if normalized cost decreases, the simulation will cost less completely regardless of its speed. So it doesn't matter what your normalized runtime is. If one option has half the normalized cost of another, you know that to compute however many seconds of flow time you need, that option will cost half as much in the long run. So now that we have these two normalized variables, the final step is to plot them. The Prichard diagram represents these two variables as a Pareto front. Now, if you're not familiar with a Pareto front, any point along the front, which is represented by the solid blue line, is an efficient solution. So remember, this is multi-objective optimization, so there is no one objective best, but based on your current constraints, the one that's best for you might be one of those three on the front. You might notice that there are clusters of tightly grouped points. Those are the results of undersubscription testing. So, you're not seeing as dramatic of a change from that as you are from, say, jumping from one node to two, but it is definitely noticeable for most of those points, the difference that undersubscription makes. Generally on this plot, node count is increasing from right to left and bottom to top. So you can see it labeled on that Pareto front, where the furthest right is one node, the next one over is two nodes, and the final one is three. The points behind the front aren't labeled, but we aren't too worried about those because they're just objectively bad. There's no reason you would want to choose one of those. So this simplification, this plotting method, enables easy hardware selection based on whatever your current constraints are, whether speed is more important, cost is more important, or perhaps a compromise of the two is the best for your current situation. So in this instance, the Pareto front, the Prichard diagram, narrows down this whole sea of data of however many data points that are there to just three potential options. So for example, if cost were the most important thing for you, you could look at this plot and see, okay, well, what is the lowest point on that Pareto front? And here you can see, okay, it's 1 of machine gamma with an undersubscription of 117 cores per node. And in this case, I just happen to know that gamma has 120 cores, so you're looking at 3 cores left free. Additionally, it can also be useful to use the Prichard diagram to kind of guide future benchmarking. So perhaps you haven't finished your benchmarking and you're not really sure where to test. Well, here we could look at the plot and see, okay, while machine beta was not on the Pareto front at any of these stages, it does kind of have this downward trajectory, so maybe it would be worth testing a little further this way. And I think in this case, machine beta, this is already one node, so you really can't go any lower than that. But it illustrates the point that you can look at trends in the plot and use those to dictate which you test next, because it's practically impossible to test every possibility for every variable and to not spend weeks and thousands of dollars on the benchmarking. It can be interesting to plot multiple models on the same Prichard diagram just to see how their behavior changes between the different core types and as you scale. So here I've plotted three different test cases on the same Prichard diagram. Models 1A, 1B, and 1C are just different versions, different meshes of the same computational fluid dynamics model, where model 1A has around 300,000 cells, 1B has 2 million, and 1C has around 20 million. You can see here where model 1A is at the bottom left, 1B is in the middle, and 1C is at the top, that as cell count grows, scalability improves. So model 1A, with its very steep Pareto front, shows poor scaling. You really have to throw a lot of money at the problem in order to get a little bit more runtime. In order to move it a little bit to the left, you're going a lot higher vertically. Model 1B shows moderate scalability, so it's fairly diagonal. One interesting thing to see about Model 1B is that I performed one test with many more nodes. So I think these points are in the range of maybe 2 to 4. I think it's probably 1, 2, 4, 8 nodes. And then this one up here was 18 nodes. And you can see that that top point is much higher than the square below it, but it's actually to the right. So it's much more expensive, but it's slower. This is possible with many scientific codes, is that you get to a point where adding more cores slows things down. So that really underscores the importance of performing this optimization so that you're not accidentally picking a node count where you're wasting money, where if you ran fewer nodes, it would be cheaper and faster. Finally, Model 1C shows favorable scaling throughout the range. I mean, its Pareto front is very flat, showing that really there would be little sense at running at below this maximum node count tested, as you're not saving much money, but it is running a lot slower as you go this direction. One interesting thing to notice in Model 1C is something called superlinear scalability, where these two triangles, it's a little hard to see from this at this zoom, they're not actually on the Pareto front, they're just above it. So as you increase node count going to the left, you actually get where this point is gaining more speed than the number of cores being thrown at it. So if we doubled cores from this point to this point, you're gaining more than double the speed. So that's another case where, on this side, you could pick too many nodes and be wasting money, but on this side, you could pick too few and be wasting money, because you're just getting free speed. You're saving money and you're gaining speed by going to this point. In conclusion, in HPC, a small improvement to efficiency can be very consequential. You could be talking about saving days of time and thousands of dollars, so it's very important to optimize. However, with traditional or methods that are not terribly well thought through, it's really difficult to find an optimal hardware configuration just because of the amount of raw data you get when you're dealing with 3 variables and 2 objectives. Consequently, an effective and intuitive optimization technique is absolutely necessary in order to effectively and easily optimize. The Prichard diagram accomplishes this by condensing all of the variables in both normalized objectives into a single plot. To date, its use has saved the Liberty School of Engineering roughly $50,000, and it's continuing to save us money as we run new CFD models going into the future. Looking forward for this research, we're hoping to allow the prediction of optimality without benchmarking. So every new model we run, we still have to benchmark it, and we're hoping we can rely on the vast amount of testing data we have in order to predict the best hardware for a given situation without having to run through the gamut of benchmarking. With that, my presentation is complete, and I will be present in the virtual session to answer any questions you might have. Thank you.